Hi, everybody, and welcome to our webinar on ClickHouse data management internals. We'll be talking about MergeTree storage, merges, replication, the mysterious DDL replication queue, and other good things. So this is really going to be digging into internals of ClickHouse in a big way. I'm delighted to see how many people have signed up for this. Before we dive in, let me just cover a couple of housekeeping items. So first of all, this video is being recorded. Let me just double check that. Yes, so it's screen sharing. And in addition, what you see on the screen will be recorded along with the audio. We will send you an email if you signed up, and even if you didn't attend, you'll get an email with links both to this recording as well as the slides. So you don't have to take frantic notes. It'll be coming to your email pretty soon. The other thing is that we do have time for questions on this. I should be joined shortly by my partner in crime, Alexander Zaitsev, who is our CTO. And if you do have questions, feel free to pop them up in chat or the question and answer box. If they're relevant to what we're on, I will jump in and address them. Otherwise, we'll have some time at the end. We'll be glad to answer questions. So with that, let's get going and do a few introductions. So I'm Robert Hodges. I'm Altinity CEO, but for the purposes of this talk, I am a database and specifically a ClickHouse geek. I've been working with databases for about 40 years. Other folks who contributed in profound ways to this presentation are, first of all, Tatiana Saltykova, who is our outstanding support engineer, has run ClickHouse for years, does our trainings, including the administrative ClickHouse administrative class, which we'll talk about at the end, and prepared a lot of the content that is in this talk. Alexander Zaitsev is our CTO. He is the architect of Altinity.cloud and has run and operated and worked with ClickHouse for many years as well. Altinity is an enterprise provider for ClickHouse. So among other things, we operate Altinity.cloud, which was the first managed ClickHouse that was developed for the Amazon public cloud. It runs in Google and Azure as well these days. We're also authors of the Kubernetes operator for ClickHouse. If anybody here uses Kubernetes, there's a pretty good chance you're using our operator already. If you're not, you should be. So we have long experience in ClickHouse and particularly operating very large numbers of clusters at scale, both directly for customers and also helping customers do it themselves. So that's what we do. Enough about marketing. Let's dive into the presentation. By the way, if somebody can just post in the chat to confirm that you have that the audio is good, that would be great, and that would be very helpful to see that. Great, thank you. Just got a confirmation from Arthur. Thank you very much, Arthur. All right, let's dive in. So for those of you that have not heard of ClickHouse, it's a very popular open source real-time analytic database, here described as a SQL data warehouse. You can think of that, but it particularly shines for real-time access to data and query results. By real-time, we mean that for human analysts, you can often do queries across potentially very large amounts of data, get an answer back in a second or less. If you set things up correctly, for example, using pre-aggregation, you can get query results back in as little as 20 milliseconds, which is the kind of time that is required to feed data warehouse information into a software process. For example, it's rendering a page and delivering recommendations. Some of the features that make it very powerful, like MySQL, popular online transaction processing or transactional database. It understands SQL, it runs practically anywhere, and it's open source. In the case of ClickHouse, it's Apache 2.0, which is very flexible license. And then like most data warehouses today, it stores data in columns. It's very, very good at parallelizing execution, including using vectorized instructions on Intel CPUs, or Intel architecture. and it scales to many, many petabytes. So we ourselves run instances in the cloud where people are attaching to individual servers up to 40 or 50 terabytes of block storage. And of course, you can extend it, as you may have seen from other webinars we've done, you can extend it to S3. It's very, very powerful. So enough about ClickHouse. What are we trying to do here? Well, this belongs to a series of presentations that we have done over the last couple of years, where we try to present what's going on under the covers in ClickHouse. And the idea is if you understand what ClickHouse is doing, you can make it faster, you can use it more efficiently. ClickHouse has a relatively simple execution model, and the storage, I think, is less simple, but as far as the execution, practically anybody can understand how it works given enough experience. That knowledge allows you to make faster and more efficient queries. And in the case of storage, you also understand the costs of different types of operations in a way that allows you to operate cost efficiently. So that's what we're doing here. The knowledge is, we try to make that as accessible as possible. Let's dive in. So what we're going to do here is start with fairly basic, sort of the basics of MergeTree, which is the one table to rule them all in ClickHouse. It is the workhouse table for big data. ClickHouse, as many of you know, has many table types, and is great at doing things like being able to select data directly out of Kafka topics, being able to maintain data in memory, being able to maintain dictionaries. These are different types of engines that allow people to access data. But for this talk, we will be focusing entirely on MergeTree. So let's look at a MergeTree table definition. It's like SQL, except not like SQL, because there's some important differences. Looking past the data types, which of course we typically use the native data types for ClickHouse. That's just a tradition based on how ClickHouse grew up. The key thing that you see when you look at a ClickHouse table definition is this engine. So ClickHouse, as I just mentioned, has many of these, but MergeTree is the one that we'll be studying today. It, of course, has variants. For example, aggregating MergeTree or replicated MergeTree. Under the covers, they all behave essentially the same way at the storage level. So what you learn here applies to all these table types. MergeTree table engines MergeTree tables need to have some guidance on how to break the table up into pieces. And this is important because MergeTree tables can be very large. So we need to give ClickHouse a bit of a hint on what's the most obvious way to break this up. So for example, in this particular table, we're breaking up by months. We're also telling ClickHouse how to construct what's called a primary key. We'll look at this in more detail. This is used to locate data. It's basically a sparse index, and then how to order it. Ordering is critical in column-based databases because it affects what data is contiguous. In other words, which rows are contiguous with which other rows. This makes a huge difference when you're doing a query because it limits the amount of data you scan. The other thing that it does is it can have a profound effect on compression. So ordering is also very important. So let's just start. We're not going to talk very much about query execution in here, but I would like to start with a simple example and show you what happens, and then we'll use that to inform the discussion of what's going on in under the covers at the storage level. So when you do an insert, and this is a very, very simple example of inserting into some random table with some made-up data, this insert is going to be parsed, and then ClickHouse does a certain amount of planning. It doesn't have a query-based optimizer, so it's not really going to do some sort of cost-based plan, but it figures out how to split the work up, and it can parallelize it. That's a very important feature, but we won't talk about it here. But then we're going to go ahead and load the data. And what happens when you load a block of data into ClickHouse is we construct what's called a part. In other words, one of these chunks of the table, we construct it fully in RAM, and then we blast it out to disk. So we're going to go ahead and construct the part so basically a representation of the part as it will appear on in storage, including sorting it, including compressing it, and then basically we write that out to storage. And that process is typically pretty quick. In fact, for a very simple query like this, it says 27/100ths of a second. That's actually mostly measuring latency between me and my ClickHouse server, which is some distance away. So it's very quick. Let's look at what happens, what's then happening down on at the level of storage. So inside the table, as I've mentioned, the data are divided up into parts. So, and they are the parts are within partitions. And just to flip it back, we have this partition function, this partition by clause, and this says, okay, using something in the data, let's split it up into some reasonable chunk so that ClickHouse will be able to create a set of parts that tend to be about the same size across all partitions. So when we look at parts, what we'll see is that in this particular example, all the rows in any individual part belong to the same month. There can be many parts for the month, depending on, if you have a lot of data in a month, you may end up generating many parts. In fact, initially, every time you do an insert, you will generate at least one part. And then if we look more closely at the columns will be sorted by the carrier flight date departure time that we gave in the order by clause. And then we have the sparse index, which finds the rows by carrier and by flight date. Often when you define ClickHouse tables, you just say order by and don't bother to say, to give a primary key index, in which case it just uses the columns of the order by. But it's for large tables, it's important actually to keep the index, to have the index have fewer columns. One of the big reasons of that is that this sparse index is designed to be able to fit into memory, which is an important feature that allows you to to find things quickly, even when the table is extremely large. So let's look at the actual composition of the part. So every time that, one of the cool things about ClickHouse is, unlike the storage that you see in, for example, InnoDB on MySQL, which is basically a table space and kind of opaque. When you go to ClickHouse, you can actually see the individual files on disk. This is what's called a wide part, and a wide part has a file, actually two files for every column. We can see them here. They're in modern ClickHouse versions. There's a .mrk2 file, and that is actually an index into the starting point of a block of compressed data, and that index is often called a mark, and you have a compressed block. So what this does is it allows us to use the primary key index, which is the structure we show on the left, and locate particular blocks efficiently. There are other ways to index data. You can use secondary indexes. You can also do what's called pre-where. Well, ClickHouse will effectively take a column which is compressed, and if you're filtering on it, or for example, you have it in the where clause, ClickHouse can use that as an index as well. But these marks basically give us a way of indexing particular chunks of compressed data for each column. So this is basically what you'll look at, and we're going to look at in more detail at how some of these names arise. You can see this kind of complicated name for the part above. We'll look at that in more detail in just a second. But this is your basic structure. You're going to see this. There are a variety of different ways that ClickHouse can actually store things. We'll talk about those, but you'll essentially see this structure no matter what. There is one exception to that, and for small blocks, ClickHouse will use what's called a compressed part, or excuse me, a compact part. And compact parts, instead of having two files for every column, they basically collapse the structure down to a much smaller number of files, which means that we don't have to have open a bunch of file descriptors for a part that is small. We won't talk further about compact parts, but they're an important feature for ClickHouse performance. So one of the things, as I mentioned, that I love about ClickHouse is you can actually go look at the data. And so if you have a ClickHouse server, what you want to do is get onto that host and where it's running and go with presumably sudo to root and then go to varlib ClickHouse. By default, that's where your storage lives. And if you look under that, you'll see a bunch of directories, but there are three that are particularly important. There's the data directory. And if you go into this, this will allow you to chain into the data that is actually contained inside your tables. You can find them and locate and see the parts and go into the parts and look at them. You also have the what's called the metadata table. That's where all our SQL definitions are stored. And then you have the store directory. Excuse me, I said metadata table. I meant metadata directory. And you have the store directory. And this is a relatively new structure in storage. It is used to also to store table data, and we'll dig into that in just a second. So one of the first things that you learn about as you start to look at these structures on disk is the difference between what are called atomic and normal databases. So normal database is the older format, the original format for ClickHouse, and it basically just laid things out on disk without having any level of indirection. And so if you're using, for example, the default database on an older server or a server that's been around for any length of time, it will, for example, be a normal database. And what that means is that these data structures that I'm talking about, you can go out and just walk the directory structure and just go, find the database, that's a directory, find the table, that's a directory, and then look at what's in it. You can actually see the parts in their constituent files. So this structure was nice because it was really easy to understand, but it had some disadvantages. And one of those is that there are operations like renaming tables or exchanging tables. This is where you prepare a new copy of a table and you want to switch it atomically with a copy of the table that you already have. Those cannot be done with that structure. So because you basically have files, the logic to scan them depends on the directory structure. If you move things around, it's gonna screw up queries. You'd basically have to stop. It makes it much more difficult to do these operations atomically. So as a result, a couple of years ago, maybe 3 or something like that, ClickHouse introduced the notion of an atomic database, and this uses some indirection, where basically all the actual files themselves are stored in varlib ClickHouse store. And then as we walk the tree, and we'll show you examples of this, what we'll get is actually soft links that point us to the right location in varlib ClickHouse store, but the data is actually stored there. And then what we can do is if we need to do an exchange, we can just flip the links around, and without moving data and in a totally transparent way, we can do these operations like exchange table. Let's look at that more deeply. So let's go into a normal database. And yeah, oh, great point from Eugene. Yeah, and I want to make this clear. So what I said was the normal database, if you're looking at default for an older server, you will see that it's a normal database because ClickHouse doesn't automatically upgrade it for you. That's the case actually on the server I used for this talk. But if you install a new database from scratch, default will also be atomic. Default is as it sounds like, the default database that just appears in any new ClickHouse, and if you do nothing else, your tables will appear there. So let's look at a normal database. So what we're going to do is try and find it. So the first thing we'll do is we can just do an ls minus l. Actually, that should be an ls minus ld to keep it from expanding, but into the directories. But we'll see a default directory. That's where the tables are going to be under that. And then we'll see default.sql, and that will be the command to create that database. Now, one of the things that ClickHouse has that helps enormously in these explorations is it has extremely good system tables, the best of any database I've ever worked with. And here's an example. So if we want to find out details about where this, where the default database is located, we can just run this query on the system.databases table. And here's what we see. We're going to see the name default. It's ordinary database engine. There's the path, and then it's the UUID, which is empty. And what this means is this is not an atomic database. Atomic databases assign UUIDs to every entity so that they can move things around. The UUIDs don't change even when they're pointed to in different ways. So this basically gives us the info. We could walk the tree ourselves, in other words. That's how I did it here. Got onto the host I was using root, or I can just ask system.databases and it will spit out the location for me. So let's see. So if we go further into it, so look at what's underneath here. So let's see. Default or lib. Just 1 second here. I want to make sure that I have. Okay, I think I have. My apologies. There is a slightly different. This is not the. Oh, okay. So this is finding a error on the slide here. Brief discombobulation. This is finding an atomic database. So if we go look at an atomic database, and this should say not default but system star, what we will see is that this metadata at system actually contains a soft link, and then it points to this sort of horrible looking location under varlib ClickHouse store. This is the way that the atomic database works, because in fact it's being stored in the store directory under the UUID that identifies it. So, and when we go and run that same select on system.databases, we'll actually see the UUID filled in. So this tells us, tells you where to go inside varlib ClickHouse store to find this, the file that represents, or the directory that represents this part of your stored data. So if we want to find a table in an atomic database, let's go look for the system query log, which is a very popular one. If you do any performance, it's one you will probably look at. So we'll go in here, and we're going to do an ls. And once again, the structure of the database and the tables is visible under data. And so we'll see system and query log, but what we'll see again is that entry is there, but it's actually a link again to something located in storage. And so if we now go to system.tables and ask the same question, where is this thing located? We will see a very similar bit of information to what we saw in databases. We'll see that it's a database system table name query log, and here's the metadata path. So here's where the metadata path is located. You'll see that's our query log table definition. It's also out there in store. And here's the data path. Notice that it says data paths. Well, the reason for that is that there actually could be multiple locations of the data, and that would be the case if we were using tiered storage and had multiple disks which contain the data. So ClickHouse tracks this and makes it possible to locate all of them. Let's go ahead and do the same operation in an ordinary database. So let's go look for a table on time. This is flight data. And here's what we see when we actually do an ls on this. So this was, we see a couple parts under it. Those are the part names. We see the detached directory. Detached is really important. That's where we'll talk about this command, but you can detach parts, which means you remove them from the table, and then they just get stuffed into this detached directory, and ClickHouse forgets about them. And then here's a file that shows the format version of the part. And again, we can ask that question from system.parts. We can go and find out about information of specific parts. You can also do this in an atomic database, and this will give you the name of the part. I'm just getting a few of the things, but the key thing is the path where we can find it. So once again, in an ordinary database, we're just walking a directory tree on the Linux file system. And under each directory, we actually find the files. In other words, you can imagine this, and we'll talk about this in a little bit more detail. You can imagine the directory just having links, hard links to that, to the actual file data. Okay, so now we've talked about parts, and I mentioned that every time you do an insert, the parts get, it creates a part. Now, if we just left it that way, that would be really bad. And the reason is that small parts are inefficient for queries. They're inefficient in many ways. That large part, or sort of the wide part, I should say, that I showed you has lots of files in the part. So the data set that I'm using, this on-time table, has about 109 columns in it. So that means there are going to be at least 218 files. Those consume inodes. They take time to open. They take time to traverse. So what ClickHouse does in the background is, as soon as you insert stuff, it begins a process of merging the data. And we'll talk a little bit, we'll show it, sort of more of the details in just a second. But the basic idea is that there's a background process, and ClickHouse is from time to time scanning the parts, and then it recognizes that, hey, these two parts right here can be merged. And you see how they're numbered. So this is year 2018. It's actually already had some merged stuff. The original parts were numbered 3 to 12. That one means the data underneath it has been merged once. Here was another one where we had original parts that were numbered 13 to 24, and they have been merged once. ClickHouse goes over this and says, hey, I can combine these two parts, and it creates a new part. And you see how it's numbered here, 3 to 24 and 2. That means the data in this has been merged twice. So you can actually look, and even these file names show you in a sense, allow you to track the provenance of the data. Something that's really important to realize that when this is going on is, during this merge process, ClickHouse will basically bring the parts into memory, sort them, and then spit them back out onto disk. So as a result, during a merge, your file system will have the original parts, and it will have the new part, and so you have double the amount of disk space. And that's an important point, because what it means is that because of the way merges work, you always need to have some extra disk space to allow them to take place, because they're going to consume extra disk space. What happens to these parts? Well, the old ones will, ClickHouse will go ahead and mark them as no longer active. And then after a few minutes, and I believe the default is 8, they will just be wiped out automatically. So this extra storage that you're using will go away. But if you have very active merging, what that means is you need a buffer to ensure you have room for these parts and don't run out. Otherwise, merges will just stop. So here's how the algorithm works. So there's a feature called a part of ClickHouse called the merge selector, and it's scanning the tables and looking for parts that can be merged. And then there's a merge executor, which picks a merge, and so it schedules the merges because they need to happen in a particular order. The merge executor picks the merge and then runs it. So it goes ahead, it grabs the data, pulls it into memory, resorts it, and spits it back out again. You can figure out which merges are running right now just by doing a query on system.merges. This is another one of these wonderful tables. And then you can actually see, this is an incredibly useful table that you need to enable, but it's called system.partlog. This allows you to see the exact record of all merges on all parts. And for tracking the history of what's happening with your data, it's incredibly helpful. You can see how, like, for example, this can show you the level of merge activity that you have over time. So it's a very useful table to figure out what's going on in merges. So let's go back and kind of look what's on disk after a merge. And in this particular case, we're going to go back to on time, look at the parts, and I'm just showing a few of them, but we have some parts. We have a part 1515, that's see how that's marked 0. That was inserted. There's another one 1616. This is what they look like when they're inserted. This ClickHouse is keeping account of these. And then this part between them is actually a merged part that contains those, contains those parts and actually some others as well. So we can find out about what the state of parts is by looking at the system.parts table, which is, again, super, super useful for one that I spend a lot of time looking at. But what we see here when we run this query is we can see that some of the parts are active. So the merged part, the second row, that's actually the part that your queries will see. You have the other ones which are marked 0, which means that ClickHouse is done using them and they're just waiting to be removed. So, and you see the level here, those numbers happen to look the same, but don't be fooled. The level is the number of times the data has been merged. Once it's merged, and it can be merged 2, 3, 4 times, you will actually see the level count increasing each time. And then these other things are just like number of rows. See how this one, the merged one, has much larger number of rows inside it than the parts that it was merging from. So this is all visible, and you can figure out what's going on. It's a really important part of management of storage in ClickHouse. So we've gotten through a big chunk of how this works, which is, basically the on-disk formats for storage that are most commonly used. Let's talk a little bit about manipulating parts and mutating the data in them, because these are really important topics for ClickHouse. So parts are, people sometimes say that ClickHouse doesn't support transactions. And that's kind of true if by transactions you mean an ACID transaction. However, what ClickHouse really does is it actually has a transaction model that is based on parts. And the thing that ClickHouse does is when it writes a part, it's always atomic. So ClickHouse has pretty strong guarantees that you won't get what you might call a torn part. If you know about disk formats, you talk about torn pages, where a page is partially written, and then some unlucky application reads it and falls dead. ClickHouse really does not do that very often. So when you write a part, ClickHouse will write it in full or not at all. Moreover, the part will be inserted in such a way or added to the available parts in such a way that queries will not see a part while it's written. So you don't have dirty reads on parts. There are a large number, sort of, consonant with this, there are a large number of commands to manage parts. This is one of the simplest ways that you can move storage around and change it. Let's just pick a couple. So for example, if you want to get rid of parts or entire partitions, you can just say alter table, drop partition. These are, by the way, these are alter commands. So, and what will happen here is, depending on, what you specified, you'll, it will go ahead and drop it. This is extremely fast because all it's doing is basically unlinking files on the file system. Similarly, you can detach a part, which means that you can remove it, and what it does, it doesn't actually move the data, but it basically pushes the directory which has the links to the underlying files, pushes it into that detached directory, so on and so forth. Lots of other commands here. So one of the reasons these commands are important to know is they're extremely fast, because they don't require, if you're just doing things local to the disk, ClickHouse is actually just going to be playing games with moving links around. It's not actually going to move data in general. So some of these are not, may cause mutations, but in general they do not. So here's some examples of how to use them. So important thing is you need to be able to identify the partition IDs as well as the part names. And for that, of course, there is the system.parts table, and here's a simple example which shows the a couple of operations. So for example, where we're going to go list the for the default default database on-time table, we're going to go list the partitions and their IDs and their names, and then use them in a couple of alter table commands that operate on those structures. So for example, we have the name of a part, so that name column, we can use that to go ahead and detach the part. So you see the 2018, 15, 26, if we issue this command, it will detach it. So it'll move it to that detached directory, and ClickHouse will, basically, if you then run a query, ClickHouse will just forget that it was ever there. Another thing we can do is we can drop a partition. So we can just give the ID, the partition ID, and then ClickHouse will go through and it will drop every part that is in that partition. And so they will just vanish. And these commands, they might take a second or two if you had a huge number of files, but they're really, really quick. So for example, when you're truncating a table or you want to drop the last month of data, issuing this command, for example, if we wanted to get rid of the the data from year 2018, it would be it would vanish in an instant. And this is a good time to actually talk about hard links, which is the way that ClickHouse plays these tricks to move things around quickly. So for those of you that are Linux fans, you already know about this, but the basic idea in Linux file systems is that files themselves are just blobs of data, and they're stored using inodes. And then when you construct a directory is another kind of file, but it basically has links, what are called hard links to the inode, which has the directory. What this means is that you can have a directory, if you use hard links, you can have a directory which, or two directories that actually point to the same file. When you're using those directories, you cannot tell this, but what's really important is that if you delete the file, for example, in directory foo, it does not disappear in bar, because there's still a link to it, and the Linux file system maintains a reference count on them and deletes them when they're gone. So how can we use this feature? Because you'll see it coming up. And one important way that this comes up that is important to understand if you do backups is this command called alter table freeze. And what this does is it will give you a snapshot of a table that is stable. In other words, things won't change. Files won't get deleted, like parts won't get deleted, new parts won't get added while you're copying it for a backup. So here's an example of if we wanted to back up the default.ontime table, we'd say alter table default.ontime freeze and give it a name. And what it does out there is it's a very, very quick operation, because it basically goes out and there's a thing called a shadow directory, which you'll see out, if you go traverse the file system, it'll just create a directory there. And then you'll have parts underneath it. And each of those parts won't actually have their own data. They'll just have hard links back to the original files on the file system. So now ClickHouse can go its merry way. It can do merges. It can do all kinds of other things. But what will happen, even if ClickHouse itself drops a part, it won't disappear because there's a hard link to it. Alter table unfreeze reverses this. It wipes out the hard links, and basically the files then, if ClickHouse already deleted them, the files would then be released and be returned to storage. Why is this important? Well, if you do an alter table freeze, you're basically committing storage. And so as long as that shadow directory exists, the underlying files cannot be deleted, and you'll continue to see them booked on the file system. But ClickHouse itself will not know they're there. ClickHouse will say, "Hey, my storage, you've got 100 gigabytes of storage active." But then when you go to the file system and look and do like a df command, you might see, hey, there's 120 gigs of storage allocated. That remaining 20 gigs could be in shadow directories. So this is an important thing to understand, because it affects your management of storage. Let's talk about changing data. So that's the other thing that we can do. We can manipulate parts, but then we can actually make changes to data that will affect parts. So there are many commands that do this, and it's beyond the scope of this talk to do them. But let's just take two simple ones. Alter table delete. So what this is going to do is it's going to delete data, delete rows from parts, but it's going to do it as a background operation. So here you see mutate. We call this a mutation. It basically gets enqueued. I'll talk about how it runs in just a second. And these could actually generate a lot of I/O. So, and there was a design decision very early on in ClickHouse history based on, practical experience that actual changes like this are relatively rare, particularly in time ordered data. So ClickHouse does it rather than optimizing to do a delete in place, ClickHouse had an asynchronous process to do it. Same thing with update. So update is another example where we're going to change data in the part, but like a SQL update command, it will only affect a discrete number of columns, like maybe 1 or 2 columns, but not all of them. So there are significant differences between these two types of mutations. So in the case of the update, ClickHouse is actually pretty clever. What it does is it will go to the old part when it has to run the mutation. So that's basically run the query to select the data and make the changes. It will only change those columns which are in the update command. And then it'll generate a new part which contains new files that it has written. For example, maybe there's one column that's changed here, but all the other columns, this new part will just have hard links back to them. And then what will happen is the old part will no longer be active. It'll be replaced. And in due time, like 8 minutes, it will just disappear. So this means that actually alters can be relatively efficient because they only actually touch the data that's in the column. And so even for, and this is something that's good because in large systems, you don't want to have to rewrite all your data just to fix one column. Deletes are different. Deletes are going to go through and they're going to remove the whole row. There's no choice there but to rewrite the entire part. So deletes are very expensive. You take the old part, you run the query over it, and you write a new part that basically has dropped all the data that's and there's no sharing of hard links or anything like that. The old part just disappears. So this is a relatively expensive operation. So how do you see when you run one of these commands, it will instantly come back, alter table, delete, and under some conditions, and then you'll be saying, okay, what's going on? So the first thing you can do is you can go look at system.merges to see if your mutation is being executed. And then the other table, which people really use a lot. Oh, here's a great question. What's the memory implication? Okay, I'll get to this. Thank you very much for that question. We'll get to this in just a second. So we'll use system.mutations. This is another valuable table to see what's the status of this particular mutation. And what it will, we can go ahead and select from it, and it will basically tell us all the active mutations and where that not is done, where they haven't completed yet. And then there's actually a really important, so mutations can sometimes fail for a variety of reasons. So we can actually go look in the system.mutation table, figure out why they're failing. Here's the query to ask. And this will show you if something's failing. And then if things go really wrong. So for example, you have a mutation which turns out, a common problem we'll talk about in a second is mutations, because they're heavyweight, they may take, if you issue the wrong command, it could actually bog down your server for a day. So that's not good. So there is a way to kill a mutation. And basically what you want to do is you say kill mutation, that's a command, and then where, and these are basically selectors that must match on something in the system.mutations table. If there's a match, they'll stop it. And it won't stop right away because you can't, get, ClickHouse may take a little bit, way to notice it, but that is, that's not such a, but it will eventually, it'll eventually get killed, unless there's a bug. Every now and then something doesn't want to get killed, but they're pretty rare. So there's a question here: what are the memory implications for accumulated hard links of deleted files over long periods of time? If by memory you mean RAM, basically none, at least that I can think of, because once ClickHouse, for example, if you have something that, if you do an alter table freeze and something is stuck in the shadow, in a shadow directory, if once ClickHouse gets rid of the part, as far as it's concerned, that part no longer exists. It does not know that somebody else is holding hard links to those files. So there's no implication for the ClickHouse server whatsoever. Where the implication does occur is for your storage. And there's two things you want to be careful about. One is it's just using up space on the disk because, hey, we got to store the bytes somewhere. So that's still booked, and that can cause you to get a file system full condition. The other thing, and this is a little bit more subtle, is going back to the picture, it's burning up inodes. So these inodes are limited. They're a limited resource on Linux file systems, and in fact, all Unix-based systems, you can run out. And this can happen if you have a lot of small parts, sort of a ridiculously large number of small parts. You can run out, and then you have a serious problem. Okay, so let's talk about some problems. Now you know enough about MergeTree that we can talk about some problems and how to fix them. Common problem, too many parts. So what will happen, this is an error you get if you're just generating too many parts inside, basically just jamming a bunch of small parts into a table partition, and then ClickHouse falls behind on doing merges to collapse them. So there are MergeTree settings that you can look at, and I don't have them listed here, but they basically will allow you to change the merge process. To be totally honest, when you get this problem, the best thing to do is to actually change your application. So let me give you an example. If you have tenant data that you're loading into a table organized where you're partitioning by month, go ahead and make sure that any tenants that you're loading for each insert, you just have data for that month. Otherwise, what's going to happen is if you just load tenants and have the time be random, like load them over a period of years, you will generate in a single insert, you will generate a part for every month that you have represented in that block. So this is a pretty serious problem that is usually cured by applications. There are ways to to play around with settings. We deal with this a lot in service, in support cases. But what we're really doing there is actually helping somebody get around a problem that's created by their application, and it's usually generally speaking, it's a short-term fix, just so that you can get over some like loading a new customer or something like that. But what you really want to do is go back and look at your application. Start time. This is another really important thing. I mentioned that we saw the wide parts and how many files they have, so 2 per column minimum. If you have null values, you will generate additional files to track those. These are create a bunch of files, and what ClickHouse is going to want to do is when it starts up, it's going to want to open all those files and have a look at them, at least get the file descriptors. So if you have a lot of tables or you have small parts or small partitions, ClickHouse can take a very, very long time to start up. So there's a discussion going on right now on the ClickHouse workspace. Somebody has like 100K plus tables. I'm sure they had a good reason for doing that, but if you're doing a new system, don't do that. Don't have a large number of parts. Don't have a large number of tables. These will cause you to, again, there are ways you can work around it, but what you really want to do is change your application so you don't have this problem. And then another effect is just too many mutations. So, and this is because the mutation returns instantly. It does not. ClickHouse doesn't show you the cost. It just runs and then off it goes. And so what you'll find out is that you'll queue up mutations, and then you'll see one at the head of the queue because it's going to run them in order. And if you have something, if the queue gets pretty deep, they simply won't process, and you'll end up having to kill them and start over. So again, there are settings that can help to make this more efficient, but you need to be very careful. What you need to do is just be conservative about using mutations in the first place. Let's talk about a final topic. We're running up close to the hour, so I'm just going to go into replication very quickly. So MergeTree tables support replication. It's at the level of tables. It is not cluster replication. It is not at the level of database. It's table to table. So how does it work? Well, let's first of all set up a replicated fact table. So for example, what we're going to do is set up the engine using replicated MergeTree. Once again, it is at the table level. That says this is a MergeTree table and we want it replicated. How is it supposed to be replicated? Well, this structure right here on the second line where I'm waving my cursor is a path in Zookeeper or ClickHouse Keeper. And this is, this will be used to control where you go for, to understand which tables are merged. So everybody who shares this path, every table that shares this path is a replica. So that's basically how it works. And then the replica name here is just to identify the particular table to say, hey, I'm a replica on server 25. And then you get the normal partition by and order by. Important thing about replicated MergeTree is at the storage level, they are identical to normal MergeTree tables. There's just logic to move stuff around. By the way, there's a question, very quick one. How many parts or tables are too much? You usually want to shoot for something on the order of, like low thousands of parts. 1,000 is a really good number. What this really means is that if you are, using MergeTree, big parts are good. There is no problem with having a part that's 50 gigs. MergeTree is fine with that. So that's an important thing to know. So getting back to replication, how does it work? Well, you insert into one table, and then what will happen is that part will get published to Zookeeper or ClickHouse Keeper, depending on which one you're using. And then other parts or other tables will see that and understand that it needs to be replicated. How do they see it? Well, actually, let's first of all talk about what's replicated. So in the replicated MergeTree, the statements on the left are actually replicated. So if you do an insert, obviously that is going to be replicated. You just do it in one place. If things like optimize table to force merges or truncate, those are replicated. The DDL statements on the right are not replicated. So one of the things that's really important to understand is that replication is asynchronous, but it is just 1 second. Oh, by the way, thank you. Alexander is answering questions here. Great. So replication is asynchronous, but it's sequential. And one of the key roles that Zookeeper or ClickHouse Keeper plays is to maintain that queue that everybody agrees on, that this is the order of fetching parts. So what will happen is as we replicate things, we will or sort of insert things, they will be added to the queue as new parts. There's also a very important part to replication, which is scheduling merges, because remember, merges will actually change parts, so they also need to get scheduled. There is a protocol for establishing who has the right to schedule a merge, but the basic idea is that the merge will get scheduled just like any other replicated thing, and then it will get processed in order by each ClickHouse server. So this is a really important feature, and what it means is a server can be disconnected, for example, for a while, and then when it reconnects, it'll see this queue and be able to mutate or pick up all the parts. So you want to see what's going on there? Well, the system.replication queue, that is your friend. This shows the default of the database. This is a merge that's in the queue, and then what are the parts to merge? You can see the parts that will be affected. So this basically contains the information about what is going to happen in this merge. And so, if you had it inserted, you would see a different inserted block, you'd see a different type. You can get information about the state of replicas quite easily simply by querying system.replicas, another wonderful system table. And of course, it's at the replicas are at the table level, so it's not servers. It is tables that are replicas, and so you see all kinds of useful metadata here. Not much going on this one, obviously. Final topic is distributed DDL. So there is this very, very useful command in clusters called onCluster, like create table on cluster, and we give it a name. And this is actually a macro translation from the macros.xml file. What this will say is we want to run this command on every replica in this cluster. So that's important because it means that we can just go to one place, issue this command, and it will be executed. So how is that processed? Well, anything that needs to be replicated, a DDL command that needs to be replicated across queues is handled by the distributed DDL task queue. And so there's a thing called a DDL worker, runs in background, and it basically is looking at Zookeeper where there's a list of these commands and executing them. So for example, create table on cluster. And so here's the details. I won't go into them, but the basic idea is this is running in the background and processing this task. And what you can actually see these by looking at system.distributedDDLQ. So this will show you what ClickHouse thinks is in the queue. Moreover, there's another great system table. If you're using Keeper, you can go and select off system.zookeeper, and you can actually see the entries in Zookeeper itself, so you can see what Zookeeper thinks about this. And then if you need metrics, let's see if we have an example of this. We don't. This is a super useful command. If you're having problems with distributed DDL, this last command, gives you the ability to go look across all the replicas and try and figure out why somebody is not maybe not processing distributed DDL commands. They can get stuck. And that's a great, that brings up a final sort of place where bad things can happen. What if DDL gets stuck? Well, you wait. So messing with this unnecessarily is usually not a good idea. So you maybe wait a little bit more. You can also check the system.distributedDDL queue. If you do need to fix stuff, you need to go into ClickHouse and actually pull you can use the ClickHouse has Zookeeper has and Keeper has a CLI. You can go in and actually remove entries from the tree, which will effectively take the tasks away. But it's kind of messy. So the best thing is hopefully ClickHouse has a lot of features in it designed to unstick itself automatically. This last step is sort of an act of desperation. If you're a ClickHouse customer, or excuse me, a customer of Altinity, please call us. This is the kind of thing we help on. Okay, so we're running a little over time, but I'm going to stick around and answer questions. Just wrap up here. This is a deep subject, and that's why this talk has run long. There's much more to learn. I didn't even touch on things like S3 object storage, but we have a YouTube video from August. Check the Altinity YouTube channel. It's out there. How queries execute and access storage. That's another great topic. We have a video called A Day in the Life of a ClickHouse Query. Actually, a couple of the slides were taken from that. But there's also things like compact versus wide parts, looking into files, looking into column storage, caching, really important topic with storage. ClickHouse has a lot of features designed to make it run fast even with slow storage. So caching is a super important topic because at that point you're beginning to understand the relationship between ClickHouse and the storage that it manages. If you want to learn more, well, I can't think of a better way than to sign up for the Altinity class on ClickHouse administration. The materials that we're showing here are really just the tip of the iceberg for administration of ClickHouse. Many of the slides were pulled from that class, so you're getting sort of a taste of what we cover. But it's also, it's in addition to MergeTree innards, it's resource management, cluster management, all that good stuff. And then finally, where's the documentation? Well, ClickHouse official docs, obviously. Lots of great information there. Bunch of sources from Altinity. We do YouTube videos on this. Do blog articles. Knowledge base. The Altinity knowledge base has a bunch of sort of down-to-earth practical things. And then finally, if you really want to know what's going on, read the code. As Obi Ben-Wan would say, use the source, Luke. Many of particularly what ClickHouse does with storage, the C++ is quite readable, and it contains a lot of good comments that just explain what's going on. So you can go down there, and if you have specific questions, the C++ code may be the best guide. So that's it. We are done. We're a little bit over time, but and I apologize for running over. It's such a deep topic that it's kind of difficult, as you can see. You can there's a lot to learn here. And by the way, a question from one of the people listening, the links for further learning, they will be in the email that we send to you as people that attended this talk, so you'll get them shortly. Another thing you can do, by the way, is you can join our Slack if you have questions about this. Go to our website under Learn, and there's a link to our Slack channel. Join us, and we're happy to answer questions there. All right, so let's take a few questions. Here's one from Alexander Coe. I have hundreds and hundreds of directories named temp move, NNN timestamp to some table, and sometimes C errors. Alexander, do you see this message in the chat? I wonder if you have thoughts on what's going on there. This looks like something is getting confused.
Yeah, I think these are the TMP move are created when you move data between different storages. So, for example, between one disk to another, then temporary directory is created first.
Yeah, because this is actually one table type I didn't show was, or type of file that you see under parts is when ClickHouse is doing something, like when it's doing a merge, it will create a temporary file called temp merge something, which has like I believe it has the file name that it's going to be using, and so that file normally gets cleaned up. So the question that Alexander Coe just asked was, are they safe to delete? And if they're around there for a long time, I believe the answer is yes. But I would really wonder what's going on and why these things are not getting cleaned up. So it sounds like something potentially is failing halfway through. And let's see. So this is this is interesting.
Related to S3 storage, which is used.
It's S3 storage. This is a different class of problems, and it's in the S3 cache. Alexander Coe, would you mind terribly logging this as an issue in ClickHouse? This is something that you should not see, and there's a bunch of people working on object storage and would be very interested in picking this up. So please log that. Tentatively speaking, they are. Yeah. Oh, this looks like definite confusion here. It already exists and has a different inode. This looks like a bug. So yeah, please log that. Thank you, and thank you very, very much about posting for that. Let's see. Any other questions, Alexander, that we see here? I don't see a whole lot, but we'll stay open for another minute and address questions if you have them. In the meantime, I want to give huge thanks to Alexander Zaitsev, who's on this call, helped with reviewing the slides and has years of experience, and Tatiana Saltikova, who was going to be on this call, but she was traveling today and couldn't attend, but she's wonderful and is one of a number of people on Altinity that just have amazing background knowledge about this. And one thing I will say is if you want to learn more or would like to talk to us, just come over to Altinity.com. We run ClickHouse in our cloud. We run it in Kubernetes. We produce stable builds, which are designed for enterprises. People who don't want to, upgrade at longer intervals than the official builds allow. And then finally, Kubernetes. Kubernetes is our bread and butter. We love Kubernetes. We run hundreds of clusters in it ourselves, and we do the Kubernetes operator as well as other things that make Kubernetes work, make ClickHouse work well in Kubernetes clusters. So with that, I'd like to thank you all for joining us. It's been great to present to you. You'll get an email shortly giving you the presentation, a link to the presentation video, as well as the slides. Come visit us. We love to talk about this stuff, and thank you very much. Have a great day.